Hello everyone, this is Dr. Webb. So this will be the first of two videos where we look at what are called cyclic groups. So what is a cyclic group? Well, in short, we say that a group is cyclic if it's generated by just one element. So remember, we used this notation, the angle brackets around A, in the last video. And so just recall that angle brackets A, this is the set. So if our operation is multiplication, this is the set that is all the integer powers of A, where A to the 0 is the identity, and if we have A to a negative power, we're really talking about A inverse to a positive power. So, and really, when we talk about powers here, when we say A to the n, we're really talking about applying A to itself n times in this notation. So a group is cyclic if we can write it as all the elements of the group as being powers of some element A. Okay, and so if G is such a group and A is a group that where A is a group that generates it, then we say that A is the generator for the group. Because in this group, you can think about everything in this group just coming from A being applied to itself over and over and over again. Well, it doesn't matter in what order you apply the A's because you're still applying the same number of A's at the end of the day. And so what this means is that cyclic groups are always abelian, right? So if you're doing A to the I applied to A to the J, well, at the end of the day, what this is really talking about is IA's then applied to JA's. How many total A's are there? A to the I plus J. And so then you could swap the counting and have A to the J times A to the I. So all of these groups, because it's just A being applied to itself over and over and over again, you can swap the order these operations in any way because you're just applying A's. And so this is abelian. Okay, so let's talk about some examples of cyclic groups. A lot of these that we've already seen and seen that this is true, we're just sort of applying the name to it now. So the integers, we talked about that in the last video, that these are generated by 1. So that means that they are cyclic. But also z mod nz for any natural number n, this is also a cyclic group over addition generated by 1. We talked a little bit about the group 1i minus 1 and minus I. Well, this is a cyclic group where the generators, you can use either I or minus I as the generators. And so recall that we'd have I, and then I squared is minus 1, I cubed is minus I, and then I to the 4th, well, this would be minus 1 squared, which is 1, right? And so by starting with I and taking these other powers, we've gotten everything else out of this group. And so that shows that I is a generator for this group. Now, if we looked at z mod 5z star, so remember this is the multiplicative group mod 5z, well, this is a cyclic group, and we can use as the generators 2 and 3. So remember z mod 5z star, because 5 is prime, this is going to be 1, 2, 3, and 4, where our operator is multiplication, mod 5. And so if we look at the powers of 2, and then if we squared 2, we get 4. If we cube 2, we get 8, which is congruent to 3 mod 5. And then if we multiply by one more 2, 2 times 3 is 6. And so 2 to the 4th is congruent to 1 mod 5. And so in these powers of 2, we've gotten 2, 4, 3, and 1. We've gotten all of them through these powers of 2. Now, the dihedral group, that is never going to be cyclic. But if we just looked at the subgroup of rotations, the subgroup of rotations always is cyclic. And so, in fact, for Dn, the subgroup of rotations is going to be the rotation where you do it generated by 360 degrees over n. 360 over n degrees. That will generate the entire group of rotations. Okay, so let's talk about some structures that are inherent to cyclic groups. So this is an important theorem that we'll be using quite a bit. So suppose that G is a group where the identity is E and A is some element of G, and it has order less than infinity. Then we're going to get that A to the K gives us back the identity. So applying A to itself K times gives us the identity if and only if n divides k. Okay, so this isn't specifically about cyclic groups, but we're going to be using this to look at cyclic groups quite a bit. Okay, so first, let's prove the other direction. So recall that the order, this is the smallest natural number such that a to the n is equal to e. So recall that a to the n gives us back the identity, and n is the smallest positive number that makes this true. And so if n divides k, then that means that k is equal to n times L for some L. That's an integer. And so going back to a to the n equals e, well, that means that if I do a to the n and then apply it to itself L times, that's the same thing as applying e to itself L times. Well, if I do apply a to itself n times and then do that to itself L times, how many times have I been applying a to itself? Get a to the n times L. Applying e to itself L times doesn't really change anything. I get back e. So this proves the opposite direction. So now let's go the forward direction. So for the forward direction, let's suppose a to the k is the identity. That's what we're given. So then what we're going to do is n is a positive number, and so we're going to divide k by n. So by the division algorithm, there exists a q and an r, with r between 0 and n minus 1, such that k is equal to n times q plus r. So then we can think about a to the k as being a to the n q plus r. And then we can break that off. I can pull out the a to the r part, and then what I'm left with is a to the n times q, which I can think about as being a to the n applied to itself q times. Now, a to the n, since n is the order of a to the n is going to be the identity. And if I raise that to the itself q times, I still have the identity. So this is just a to the r times the identity, which is just a to the r. Well, so that means that whatever a to the k is, it's going to be the same thing as a to the r. But we suppose that a to the k is equal to the identity. Well, r can't be 1 through n minus 1, because that would mean that since r is, let me write this explicitly, if r is between 1 and n minus 1, then this contradicts that n is the order of A. And so that's a contradiction. And so the only possibility here is that r is equal to 0. And if r is equal to 0, then that means that k is equal to n times q. And so n divides k. And so that's our proof for this. Okay, so what this means is that if I take A, apply it to itself a bunch of times, and ends up with the identity, what this is saying then is that the number of times I applied it to itself must be a multiple of the order of the element. Now, an immediate corollary of this theorem is that if we ever end up with a to the I equaling a to the j in some group, then that must be because I is congruent to j mod n, where n again is the order of A. Okay, so let's prove this. So again, the backwards direction is simplest. So let's start with that. And so if we're starting off with I is congruent to j mod n, well, then that means that I minus j is a multiple of n, so n divides I minus j. And so then that means that a to the I minus j is equal to the identity by the last theorem. And then by cross cancellation, if I apply j to both sides, a to the j to both sides, I get a to the I equals a to the j. And so that's that direction. Now what about going in the forward direction? So this is kind of going completely in the opposite way. If we start off with a to the I equaling a to the j, well, I can apply a to the minus j to both sides. And that would give me back the identity. And then that can only happen if n divides I minus j, same as we saw before. And then that means that I is congruent to j mod n. And so really the proof for this really is backwards and is the exact opposite of forwards. So this really, I could have gone double arrows all the way the first time through, and we would have been done with this. Okay, now let's apply this specifically to cyclic groups. Well, applying this specifically to cyclic groups, what we get is that this says that if we have a cyclic group and the order of the element is n, well then the entire group is just the powers of A, the identity, and then the powers of A up to n minus 1. And so G itself has n elements where n is the same order as A. Okay, and this falls immediately from the last theorem. So if we know that from the last corollary, we know that if I and j are between 0 and n minus 1, and I is not equal to j, then that means that a to the I is not a to the j by the last corollary. This is the contrapositive of the last corollary. So all of these elements, a squared up to a to the n minus 1, these are all distinct. They're all different from each other. And then if I took any other a to the k, well, k is congruent to some r mod n, with r being somewhere in between 1, 2, up to n minus 1. I mean, this is the nature of modular arithmetic. Everything is congruent to something to some remainder between 0 and n minus 1. And so then by the previous theorem, by the previous corollary, a to the k is equal to a to the r. Okay, so everything in the set, they're all distinct, they're all different, and if you give me something else from that set, some other power of a that you say should be in there as well, I can say no, because k is congruent to r, a to the k is equal to a to the r, and we've already counted that. So this is exactly what G has to be, and just spelling out exactly what we saw before, any time that we have some group element A, well, the order of that element is going to be exactly equal to the order of the cyclic group generated by it. So if I start off with an element of order n, that means that when I look at the cyclic group generated by it, it's going to have exactly n members. That is all for this video. I will see you again soon.